to thank organizers for opportunity to speak. And okay, Harold is not here. So when Harold will be back, I will wish him happy birthday. Okay. So most important thing, I would like to wish a happy birthday to Harold Rosenberg. And with this, let me begin with my talk. So some of the people here already heard me speaking about counting these things. I hope I will be able to tell something new to you today. Well, if not, you tell me later that it was all old stuff. Well, so what does it mean counting manifolds? Let's look at a very basic example. Riemann surfaces, orientable, say. So topologically, there is one Riemann surface of any genus or of any, say, even negative Euler characteristic. Is it correct? Yeah, I hope. And so on. So for each chi, there is one surface. Counting is very simple. However, if we look at these surfaces, say with the metric of constant negative curvature, with hyperbolic metric, then for each genus or for each chi, we actually do have a lot of Riemann surfaces. As we know, we have a space, moduli space or Teichmüller space of dimension 6G minus 6 of different metrics, hyperbolic metrics on a surface of genus G. Well, it's quite complicated to count them. However, there is a first observation that if we put an extra assumption that the surfaces are what is called arithmetic, then for each genus there will be only finitely many of them. This word arithmetic will appear later during the talk, and I will explain more about it. So far, it's just a remark. Well, this was some basic case. Now, the general setup can be formalized as follows. We look at a symmetric space. Let me denote it. X. So this is a homogeneous space which corresponds to some Lie group. Okay. For example, it can be hyperbolic plane, like in this example, or hyperbolic 3 space, or some space like, say, SLN R modulo SON. And there are other examples. All of them are classified depending on symmetry group. So to each symmetric space, we have corresponding Lie group, H, say, associated Lie group, which is up to a finite index, is just a group of isometries of this space X. So in particular, in these examples, we have PSL2R, PSL2C, say SLN, I could actually do without P. SLN R. This is the third example, and etc. And the space X is just the group modulates maximal compact subgroup. Now we can look at what is called lattices in this group H. So gamma is a lattice in H, means it's a discrete subgroup of finite covolume. Discrete cofinite subgroup. Like, for instance, SLN Z in SLN R. And if we have a lattice, we can consider a quotient space, X modulo gamma, okay, like this. It will be a locally symmetric space or an orbifold modeled by this X space, an orbifold, which is a smooth manifold if and only if gamma acts freely. So gamma torsion free, M is a manifold. M manifold if and only if gamma has no torsion. So this discrete group gamma has no elements of finite order. And if it has elements of finite order, these elements contribute to singularities of the quotient space, but the singularities are, in a sense, well understood. And the last thing, well, not the last, but let me also fix a measure, Haar measure on a group. H, and it induces the measure on the symmetric space X. So, for instance, in hyperbolic example, we can just fix a measure in a way that the induced measure on, say, on X and on spaces M will be a hyperbolic volume. Say, the usual hyperbolic volume, constant curvature minus 1 of the total space. Or if dimension is even, like here, we can also define so-called Euler-Poincaré normalization of the measure, and then induced measure will be Euler characteristic of the quotient space. And now let me introduce two counting functions. LH of X will be the number of conjugacy classes of irreducible lattices gamma in H with covolume, so mu X mod gamma bounded by X. Okay, well, in this example, it is infinity. For any S sufficiently large. But there is another also function which I can introduce, which is the same counting function for the number of arithmetic lattices. Of bounded covolume. Well, here, okay, irreducible is just if group is a product, which is actually an interesting case, then it makes sense to restrict to lattices which are not a product, which are irreducible lattices. And conjugacy classes means that we actually want to count them up to conjugacy because we want to count manifolds or orbifolds. And if two lattices are conjugate, then corresponding manifolds are homeomorphic, isometric. So we don't distinguish them. Well, these are natural counting functions. One of the actually fundamental result of, say, Margulis, Colette, and Gromov-Shane says that for almost all spaces, these functions are equal. well, it's superrigidity theorem, which implies arithmeticity, which was proved for higher rank lattices by Margulis and then extended to some rank 1 lattices by Colette and Grosjean. The theorem says that if H is, let's say, if X is not a real or complex hyperbolic space, or complex hyperbolic space, then all lattices are arithmetic. So, well, in these terms, the theorem says more. The theorem says that all lattices are arithmetic, but okay, let me write this way. And there are several other classical theorems which tell us actually that these functions, these numbers are finite for almost all cases. I mean, okay, the number of lattices of bounded volume is infinite for real or for two-dimensional or three-dimensional hyperbolic space, but these are the only cases when it's infinite. So the classical theorems say this will be 1, this will be 2 by Wong, which was earlier than Margulis' theorem, so it's from 72. This was proved later. It says that if the group is different from SL2, no, not locally isomorphic to SL2 or SL2C. So in other words, if the space is different from 2 or 3-dimensional real hyperbolic space, then the number of lattices is finite. It's finite for any x. And the other theorem of Borel, which was proved some 10 years later by different methods, says that the number of arithmetic lattices is also finite for SL2R and SL2C. Well, and in fact, for any product of them. Well, okay, these numbers are finite, and say reasonable curiosity is, well, what are these numbers? So the question is finitely many. How many? Well, this is a very difficult question, but one can ask easier question is how these functions grow asymptotically when x is very large. So how, say, grow when, how fast they grow when x goes to infinity. It's easy actually to see here that they do grow, but it's non-trivial question is how fast they grow. Actually, this question comes from the interest to this problem first came from theoretical physics, and I often mention this, but I never try to say more. And let me just today try to say a bit more, because I think it's an interesting story why physicists are interested in all right, I want to say something about the work of Steve Carlip in late 90s, who came up with this question about counting manifolds from the point of view of theoretical physics. So, okay. write it here. There were a couple of papers by this person from UC Davis physics department in 97 and 98. So that this will be 3. What he does is the following. He wants to construct some to describe and study some model for quantum gravity. And okay, whenever you are interested in quantum field theory, the main thing is what is called partition function. Partition function has all the information about the theory. So, and Carly wrote this partition function for what? For quantum gravity, whatever it is. Quantum gravity in the following form. Z of lambda, where lambda is a cosmological constant, is given by a sum over V, rho V, exponential of some factor which is 9 over 8 pi lambda LP square V. So everything here is actually easy to define. Well, lambda is a cosmological constant, and we don't know what it is, but we know that it's very small, and maybe it's positive, maybe it's negative. But it's important in the theory. It's like a key parameter, logical constant. LP is a Planck length, so it's a well-known constant, which is like 10 to the power minus 35. Again, a very small number. Is it? Yeah, something like that. The Planck length. And this function, rho, which he is summing it, is what he calls density of topologies. So it's a number of Einstein manifolds, 4-dimensional Einstein manifolds of volume bounded by V. The same counting function, in a sense. Well, similar. So density of topologies. Number of manifolds with volume bounded by V. Maybe I should remark that this counting function, so here we like count orbifolds, but we can also define functions which sometimes denoted with a circle, the same thing, but only counting manifolds. So to make it agree with this. And okay, there is another thing here that actually this is density of topologies, but it's weighted. It's weighted by a factor, which is called an action factor. So it's weighted, this rho, by some exponential factor on volume. Again, this cosmological constant to the power minus gamma over 2, where gamma is, okay, this is correlation factor, which is actually written explicitly like some constant multiplied by Euler characteristic of the manifold minus some other constant, okay, multiplied by volume of mg. Well, the point is that this function is an exponential in volume, and there is like a counterplay between actual number of manifolds, which he compares to entropy, and this which he called action exponential correction. And so there is a big threshold between super exponential and sub-exponential growth of topology. Also, of course, here it's important if lambda is positive or negative, because if it's positive, then this is a very small number, this is a very small number, this is a very large factor. So exponential just picks up the largest volume manifold, which is, okay, Einstein manifold, in this case of largest volume, will be just a sphere. And okay, mathematically it's not that exciting. But if lambda is assumed to be negative, then we have an exponential sum. Then actually all topologies contribute, and one has to understand better this function. And the other observation which he makes in the same papers is he compares this partition function with a classical thermodynamical partition function. And there is a very nice analogy. So the thermodynamical partition function can be written as z over beta, where beta is, it's called thermodynamical beta, is just inverse of the temperature of the system. And the sum is over different energy level, rho e, again, and exponential minus beta e. So the temperature in this system is beta inverse. And if you compare it to this, so you see that the cosmological constant is like an analog of the temperature. So it can be written in this form. And then just to end up briefly this discussion, there is an important parameter of the thermodynamical system, which is called heat capacity. And this is just a second derivative of the density of rho, second logarithmic derivative of rho. So heat capacity is the following thing: Cv equal to minus beta square logarithm rho, second derivative of the logarithm rho inverse. Okay, and the comment is that it's easy to see that here there is again a sharp threshold. If rho grows super exponentially, then heat capacity is negative. And if it grows sub-exponentially, then heat capacity is positive. And somehow it determines the whole behavior of thermodynamical system. So rho e super exp, if and only if heat capacity is negative, and sub exp if it's positive. So Karlip wrote these papers, and he was quite excited about analogy between thermodynamics and this model for quantum gravity, but he didn't know anything about this function rho, which he wants to find count four-dimensional manifolds of bounded volume. However, at the time he worked, well, he always worked in Davis, but at the time also Thurston worked in Davis. And Karlip went to Thurston and asked him about this rho. And actually, it's quite surprising, but Thurston said that he didn't know, but Lubotsky was there in Davis, and he told Karlip to ask Lubotsky, and Lubotsky knew the answer. So he knew, more precisely, he knew how to prove that for four-dimensional hyperbolic manifolds, this rho grows at least super exponentially. And this kind of started the business of doing counting in various setups. So now let me show some results we have now about counting manifolds and orbifolds. Actually, now we know much more than 20 years ago. So well, I will just write some theorems and then, if time permits, discuss the argument. Well, results will be what, 4? I'm going to start with the theorem proved by Lubotsky with collaborators in response to Carl Lipp's question. So they, with Mark Borger, Sahik Gilander, Lubotsky and Moses, in 2002, they published the following result, saying that for n greater or equal than 4, when the number of hyperbolic manifolds is finite, the following is true. So we have lattices in the group of isometries of the n-dimensional hyperbolic space. And the result is that there are positive constants a and b such that a, x to the power log x, less or equal than number of torsion-free lattices in H of covolume at most x. And from above, it's also bounded by the function with the same asymptotic type. So this function counts manifolds. Let me mark. And you can see that this is super exponential. Okay, if it will be a to the power x, it will be what is called exponential. And here there is log, so it's faster than exponential. It's like factorial in this function grows, like x factorial. Like x to the power x, other way to write it, yeah? Second theorem, which was proved much later, again by 4 people, but different. I participated, then Gilander, Lubotsky, and Shalev. In 2010, we published a paper which gives the same result for the number of arithmetic lattices, but for now we can include also groups of isometries of the hyperbolic plane or 3 space, so for any n. And we have the same asymptotic type formula saying that the total number of lattices not necessarily, total number of arithmetic lattices, but not necessarily torsion-free, grows about the same way asymptotically. So here, of course, okay, these are different constants here. A and B are always positive constants which depend only on the group H. So and yeah, there is another theorem by the same authors in the same paper. The thing is that in the proof, we get estimates for these constants. One can compute some values, but they will be very bad, very bad. Like this will be very small, this will be very large, and nobody knows actually. So for instance, maybe this constant up to, probably they're actually very close, and like the correction comes in the second term. What we were able to prove, and this was the hardest theorem of this paper, is that for dimension 2, we have the limit of the logarithm of this quantity divided by, well, x log x. When x goes to infinity, we were able to compute this limit and to prove that it's equal to 1 over 2 pi. Okay, so here's another definition of pi if you want. Yeah. But maybe the main point is not that it's 2 pi here, but that actually asymptotically these constants in two-dimensional case are equal. And the proof uses a lot actually of theory of subgroups of Fuchsian groups. So it's essentially proof which works only for isometries of hyperbolic plane. We had a man in a team, Aner Shalev, who knows well, everything what we know about subgroups of Fuchsian groups. So he really worked hard for us to be able to prove this theorem. Okay, and one can ask the question if this limit exists for other groups, say for higher dimensional hyperbolic spaces, and the answer is not known. Let me now change a little bit the setting. And so far I was talking about groups of isometries of hyperbolic spaces. Now I want to talk about so-called higher rank locally symmetric spaces. So assume H has what is called real rank greater than or equal than 2. This is the setting when Margulis theorem applies, so all the lattices will be arithmetic. And okay, examples are, say, H. You can take SLN, say R, for n greater or equal than 3. For n equals 2, it's rank 1, but for bigger than 3, it's rank, okay, it's rank n minus 1. And another example is, good example is orthogonal groups, say SO, Mn, when M greater or equal than n greater or equal than 2. So in this case, the rank of the group or symmetric space will be equal to n. So okay, greater or equal than 2. We ask the same question here, and we get the following results. Okay, theorem 4 by myself and Alex. From 2012. So for higher rank H, the growth is much slower. What we have? We have yeah, we have x to the power log x, say alpha log x as a lower bound, and a similar expression as an upper bound for the total number of lattices, irreducible lattices of covolume at most x. And this is slower than exponential growth, right? Well, I will comment more about it. Let me just state one more theorem, the last one for today, which we proved recently with Ben Linovitz. It has a little different flavor, but it says that, again, in higher rank setting, at least say, x to the power gamma log x locally symmetric spaces of volume bounded by x are mutually isospectral. But actually, sorry, what we prove is we prove that x to the power log x divided by log x square of L, H, X lattices are mutually isospectral. Meaning that, okay, if it's manifold, maybe it's simpler, but it also works for orbifolds. You can look at Laplace operator on the quotient space, and this Laplace operator has a spectrum, let's say, okay, heavy restrictable compact ones. So the spectrum is discrete. And we could prove that actually a lot of these compact manifolds have the same mutually isospectral. I mean, this question goes back to, well, it goes back to much earlier, but it was popularized by Mark Katz in his paper, who asked if one can hear the shape of a drum. And okay, the key case was there to look at the Laplacian on the Riemann surfaces. And at the time of writing, Mark Katz actually said that, well, probably you cannot. So probably there exist isospectral surfaces, but we are not sure at the moment. So of course, later there were many examples of isospectral surfaces produced, and also higher dimensional manifolds. But what we observe in high rank case, that actually, like, the number of isospectral ones grows as fast as, well, asymptotically, as fast. It has the same growth type as the total number of manifolds. So, like, too many of them are isospectral. Well, there is a little bit annoying factor here, log x squared. First of all, well, you know what is log x is. Okay, it's practically a constant. But okay, not everybody believes that it's a constant. It's a very slow growing function, and we have a conjecture that it's not necessary, just we could not prove it. So the conjecture is that it's an interesting conjecture, I think, but we tried hard to prove it, but so far we stay with this log x factor. So the actual number is about x to the power gamma log x. So without any log x. You see, if you look at these theorems and kind of these physical questions which which led to this problem, you see that, okay, here we have super exponential growth, but here we have sub-exponential growth. And I think from this, at least from this thermodynamical picture, sub-exponential growth is more interesting because you will have heat capacity positive, and it's a much more natural system with such properties. So, okay, one can ask a little bit more. So where do we see this in nature? Like, because what they do is they look at four-dimensional manifolds, right? So if dimension of x is equal to 4, okay, then Carlip looked at the hyperbolic four manifolds, and here is the answer, their density of these hyperbolic topologies. But there are actually very few spaces, locally symmetric or symmetric spaces of dimension 4. And yeah, so, well, there is a complex hyperbolic one, right? But there, it's rank 1, and we cannot prove it, but we expect the same growth type. And for this type of behavior, the only candidate is H is a product of SL2R by SL2R. And so the space X will be a product of two hyperbolic planes. And I want to already mentioned it. I want to say that I find it's very interesting space. So it's a product of two hyperbolic planes. For instance, here what we do is we count irreducible lattices in this space. So we count manifolds modeled by this product of two hyperbolic planes, but they're not products. Okay, if you count not products, then you get all this interesting stuff. You get sub-exponential growth of their number, and you get that a lot of them are isospectral. But one can ask various other questions about this four-dimensional space, which has, for instance, it has curvature. It has non-positive curvature, but the curvature is less or equal than 0, and there are two-dimensional flats there. Okay, you can ask, for instance, about minimal surfaces here, and some things are understood, but I think it's far from clear, the general picture of how, say, minimal surfaces in this product geometry look like. We have some examples, but and there are other questions about this space which one can address. I have a bit of time, so let me comment. I will not be able to tell the details of the proofs, and maybe it's not so interesting because the proofs are what is called arithmetic. But you look at these theorems, and there is nothing about arithmeticity here in the statement. The theorems is about the number of locally symmetric spaces of given type of bounded volume. Well, there is reason for using arithmeticity, which comes from the super-rigidity theorem, which I mentioned here. So the structure of the proof, the way it goes in most of these results is, say, in higher rank. H higher rank. So, say, by Margulis, all irreducible lattices are arithmetic. And then, then I will say a bit more about this, but we start to use arithmetic technique. What I want to, I'm always puzzled with, maybe it's possible, I mean, there is nothing about arithmeticity here in this statement. Of course, it's what we know how to do. We apply super-rigidity and then reduce question to arithmeticity. But maybe we should not apply super-rigidity in the first step, but try to stay with the geometric problem as long as we can, and maybe even we would be able to prove something without using this number theory, which appears here. That would be very interesting. There is no any results of this type are known, but what if it's possible? Okay, now to continue a bit. So what we use then is, say, any arithmetic lattice is contained in a maximal one. Is contained in some maximal lattice. And then, the problem splits into two parts. We want to count maximal lattices and count the finite sheet covers. Count their subgroups. So it's what's called subgroup growth. And then, okay, maybe third part is to see how many of them are non-isometric. Because it can be that different subgroups are not conjugate in a lattice, but conjugate in some other lattice or in some commensurator of a lattice. It's quite interesting, actually, problem which can be solved using, okay, we solve it using Brouatti's fixed point theorem, but maybe that I will not be able to explain. So count conjugacy classes. Oh. Well, I stated it in group theoretic terms, but you can also state it in the steps. You can also state in geometric terms, like count maximal orbifolds. Here, count their finite sheet covers. And here, count isometry types of these covers. And okay, there is a technique for each of these steps. There is one interesting part here, well, part which is not in the picture, but which appears to be very useful for actually several of these steps, is that it's possible to bound a number of generators of a lattice by its covolume, and also bound its cohomology by covolume. So supplementary results, say, proved by Gilander in big generality, says that can bound rank, here both rank of fundamental group or rank of homology group, linearly by volume by volume of the space. So there are several results of this kind, but maybe this is the most general way you can state it. And it has a topological proof, this theorem of Gilander. When we know the number of generators, say, of fundamental group, it helps a lot to count finite index subgroup, for instance. So it gives you control over the covering spaces. Maybe just to end up, let me mention that in the proofs, several different techniques enter. Arithmeticity is somehow important. So there is strong number theoretical component. But there is also, say, topological proof here. And here we have some group, again, topology of locally totally disconnected spaces. Well, okay. Topology of building is used here to prove. And, well, still at the end, all this mask somehow leads to geometrical result, especially the last one I like, because it tells something about spectrum of Laplace operator on a large class of manifolds. Okay, let me end up here. Maybe a few questions.